Good morning, everybody. Our first presenter today is Simon Vandevelde. And Simon is a researcher at KU Leuven University in Belgium. And he is usually, his research is devoted to intersection between DMN standard and knowledge representation and reasoning. And his research already resulted in very interesting constraint-based extension of DMN. I mentioned this in my presentation, and Simon will probably provide more links. Today, KU Leuven researchers continue to do it not only in direction of constraint programming, but in direction of probabilistic DMN. And Simon will talk about this new PDMN version for the first time, and looking forward for your presentation, Simon. Go ahead.
Thank you very much for the nice introduction. I'm excited to open the final day of DecisionCAMP. I'm just going to quickly test if my next slide. Yeah, so the slide has updated now.
Yes.
I see it's a bit cut off from the side, but we'll manage. All right. So hello, everyone. My name is Simon Vandevelde. I'm a PhD researcher at KU Leuven. And I'll be presenting about user-friendly probabilistic decision logic modeling, which is quite a long title, but hopefully it's worth it. So what's the aim of the presentation? Well, firstly, I would briefly like to highlight the role of uncertainty in decision-making. And then I would like to show that DMN is a great foundation for user-friendly probabilistic modeling. So an introduction about myself. Jacob already mentioned a lot, but just briefly to summarize, I'm a PhD student at computer science. Currently, I'm in my 4th year, and I'll actually be defending my thesis in a month. So I'm very excited. My main research is focused on—
Good luck.
Thank you. Yeah, I need all the luck I can get. So my main research is focused on symbolic AI, and more specifically on user friendliness, because we noticed that symbolic AI has some very powerful features that can really complement today's AI landscape very well, right? With the explainability and the fact that it uses your own knowledge to reason. But in our experience, one of the main bottlenecks is still creating the actual AI system, right? Writing down your knowledge in a way that the computer can understand, but we can also understand. And so that's why my focus has been on making symbolic AI more accessible, right, to non-experts who might not be computer scientists, who might not even be IT experts, right? And so their DMN is obviously of interest, because that's exactly what the standard aims to do as well. And then we try to apply it in a more KR type of direction. So here we go. Here's a diagram that basically sums up my entire PhD, where what we do is when we try to build such a knowledge-based system, such a symbolic AI system, so we sit together with the domain expert and we just talk to them, right? We try to build the knowledge base together. And the idea of using DMN is that if we can use, I can do like that. Okay, if we can use DMN for our knowledge base, we can actually ensure that our domain expert can at least read what we are writing down, and in many cases can also write knowledge themselves, right? And this is very important because it means that when we are building such a knowledge base collaboratively, they can immediately perform a validation step. They can immediately see that what we are writing down is not necessarily what they mentioned to us, what they said to us. And so that's how DMN fits into our idea. And then these DMN tables, we put them, we translate them to our system, and then our system can build intelligent tools based on their knowledge, but again, in DMN originally. So like I said, DMN, but from a more theoretical viewpoint, but still practically applied, which is a contradiction in one sentence, but it's how I like to sum it up. And in the past, we've already done we've already researched multiple different ways, as Jacob also mentioned in his introduction. One of these is where we just plugged DMN into a reasoning engine and then saw, okay, what can we do more, right? Because it turns out that DMN models are very good at conveying a lot of knowledge, and typically we use them to go from input variables to output or to the top level decision, right? But we can actually, using the knowledge in a DMN model, do much more, right? We could also, if we already know our output, try to derive an input. Or if we know 2 of our inputs out of 3, we can see, okay, can we make any conclusions already? Or do I even need a third input given my first 2 inputs? There's situations in which something might not be relevant at all. And of course, also very important, can you explain me why something has been derived or why not? So that was the first thing that we did. And then we presented CDMN, where we thought, okay, for our use cases, DMN is great, but we sometimes need to introduce some hacky tables to ensure that we can add some more expressivity. So instead of using hacky tables, which isn't user-friendly and basically abusing DMN, we wanted to introduce constraints to DMN, where instead of always saying, so if you look at a unique table, you basically say the output has to be this value. There are cases for us in which we want to say the output cannot be this value. If you're working on a configuration problem, you might say a computer cannot have 8 gigabytes of RAM, but you don't know what amount it will have, right? And so that's what we try to do with our constraint tables. And so here, there's an example of 2 constraint tables. The first one stating that each doctor needs to, or can only work at most 1 shift per day. So again, we're not saying if they work 1 shift or 0 shifts, we're saying between 0 and 1. And then in the second example is a group assignment problem where we say, okay, each group needs between 16 and 19 people assigned to them. But again, we're not saying how many people are assigned to each group. So this was our first extension that we made. We are also, this is current research, we're also looking into how to properly handle unknown values. This is from a very theoretical standpoint, where the main idea is that, yeah, undefined is not unknown. And so this is motivated by the DM community challenge, which is called, it's below there, greeting a customer with unknown data, where you might, for instance, not know whether or not someone is married, but you still want to have a salutation for them when you're creating an email, for example. And the thing is that currently DMN is a bit superfluous on the difference between undefined and unknown, and we wanted to try and find out what the theoretically correct way to handle this would be. But again, that's very theoretical. It's a bit boring, but it's for later. This is ongoing research. I am here, of course, to talk about PDMN, which asks the question how to elegantly incorporate probabilities. And so, that's why the title contained probabilities earlier. And why do we do this? Well, because life is inherently uncertain, right? For instance, rain forecasts is always a chance of rain. You can't say for certain that there will be rain. It's like 80% chance of rain. Traffic in Google Maps, it uses statistical data to estimate whether or not there will be traffic at a specific point in time. Effectiveness of medicines, also statistical data, where you can say, okay, everyone over 18 has an 80% chance, everyone under 18 has like a 60% chance of the medicine working. And these uncertainties are really interesting to take into account when you are doing decision making, right? Because you don't want to say, okay, the medicine is effective or not. You might want to say, we know that there's a chance of effectiveness, and then try to make a decision on that. Moreover, there's also a massive shift in the AI landscape to learning/predicting from data. And these are all uncertainties, right? If you have a computer vision network that outputs whether or not it's a dog or a cat, it will always give a certainty that it's a dog and a certainty that it's a cat. And you can actually combine these or you can combine these systems with symbolic systems to achieve neurosymbolic reasoning, where you basically have both sides. And something like PDMN could also allow us to have DMN models that take these probabilities or these uncertainties into account, right? So that's the motivation for PDMN. Now, of course, there's already other systems to reason on probabilities. So here, the Bayesian network is probably one of the most well-known such systems. This is an example that I took from Wikipedia, which has quite an extensive page on Bayesian networks. I was very surprised, in a good way, of course. And so what is a Bayesian network? It's basically a graph, as you can see, where you have multiple nodes, and each node represents a Boolean variable, right? So in the example, we have 3 nodes: rain, sprinkler, and grass wet. And it's a directed graph. It's a directed acyclic graph, but so nodes can influence other nodes. And that's what's really cool about this. So we have a node rain, and basically we say, if I scooch over to right, we say that there's a 20% chance that rain is true, and 80% chance that rain is false. And then we say, okay, rain influences whether or not our sprinkler will start. And here in the condition in the table next to sprinkler, you can see that it's a conditional probability table. So based on the value of rain, the truth value, or the probability for sprinkler also changes. So if it's raining, or if it isn't raining, then there's a 40% chance of a sprinkler, 60% chance that it doesn't turn on. If it is raining, then there's only a 1% chance of the sprinkler turning on, because it's a smart system, right? And these two, sprinkler and rain, then also influence whether or not the grass is wet. And so in this way, you can create relatively complex probabilistic models that are really user-friendly, because they're very intuitive, right? It's just a graph. You draw some ovals, you put text in them, draw arrows between them, you add tables that represent these conditions, and you're done. There's some very, very powerful algorithms that can then reason on this and can try to derive probabilities. And what's interesting is that typically, or one use case for them is to reason backwards, inverse reasoning, where you might know that your grass is wet, and then you want a probability that it rains or that the sprinkler went off, right? And so in this way, you can reason backwards as well. And that's a really nice inference for these models. A different way for probabilistic reasoning is called Problog, which is basically Prolog, the logic programming system, with probabilities added to it. That's not the whole truth. So for any Problog people here, please don't shoot me, but this is the basic gist, right? So think Prolog, add probabilities. So what this means is that we have n-ary predicates. So these are just variables over domains. So instead of the Boolean variables, we can have more complex variables. And then our definitional rules can be probabilistic. So for instance, here, there's a probabilistic definitional rule that states that for each person, there's a 30% chance of them being stressed, right? And Problog then has an inference engine written in Python that can do a lot of cool inference methods. So for an example, this is quite a long Problog example, or quite a lot to put on a slide at once. But so imagine the first rule is that each person has a 30% chance of being stressed. The second rule is that each 2 people have 20% chance of influencing each other. If we know that everyone who stresses smokes, and if we know that everyone who has a friend that smokes and influences them also starts smoking, and if we then know that everyone who smokes has a 40% chance of asthma, what are the odds of people having asthma given this at these persons and these friendships? And so that's something that Problog can then calculate for us. So for instance, and these are our asthma probabilities. Now what's cool about this is that here too, Problog can reason backwards. We can give some evidence to Problog and say, I already know that I didn't include it in my slide. Oh, that's too bad. So we can already say that Angelica has asthma. What's the probability that Jonas is a smoker, right? And so these are really powerful things to be able to do with your models. And so there's many, many more probabilistic reasoning systems, but for the purpose of this talk, these are the most 2 important ones. All right. So back to DMN now, because of course I've talked about 15 minutes without talking about DMN. We can actually force probabilities into DMN, sort of, right? You could make a table like this where rain has a certainty, Certainly rain, maybe rain, definitely not rain. Or you could make a table like this where you write probability of rain, a constant between 0 and 100, where you just say whether or not the probability is higher or lower. But these have some downsides. There's reasons why you don't want to actually do this. Firstly, it's very rigid. It's you know it's hard coded, so to speak. It's not really clear. The table hides the probability in a sense. So for the table on the left, you might not really pick up that it's a probabilistic thing. And then thirdly, and this is, I think, by far the most important one, you cannot express the probability on an input value, right? So if you would want to run one of these models, then you would have to know, or you would have to input the probability of rain some way. You can't just say, I have a 50% chance of rain, or like in the example, a die has a chance of 1 in 6 to be any of the values. You cannot use this as input. You would have to actually assign a specific input value. And so that's why forcing it into DMN, while possible, has its limitations. And then for our use cases, we ran into these limitations. So what's the goal?
Simon,
Yes,
can I ask you a question back
of
here?
course.
The probability of rain or probability of something else, this is a keyword, probability of?
No. This was just an example.
Oh,
It's just an arbitrary name.
arbitrary name, but you
Yeah.
define in your in glossary, you should define the word probability or not.
Yeah. But this isn't PDMN yet. So for PDMN
Okay.
itself, we do have some fancy
Okay,
keywords.
we will wait. I will wait. Sorry. Okay.
Yeah, so what is the goal of PDMN? That's a great segue, thank you. We want to extend DMN with probabilities in an elegant DMN-like way, right? Because we want this intuitive nature of DMN to stay user-friendly. I've shown you Problog earlier. Yeah, okay, you need to know that you read right from left, and there's quite a high threshold of learning logic programming and then also adding probabilities to it, right? So we want this intuitive way of expressing probabilistic problem or probabilistic knowledge. The presence of this probability should be clear. It should be obvious that there's something probabilistic going on, and we want to reason on them throughout the entire model. And this third one is a bit difficult to explain, but I hope that I can show it to you later. And then we also wanted an inference engine for this notation so that it can do more than just exist, but it can also be run, for instance, or be sampled and stuff like that. And so that's why we looked into PDMN, or why we created PDMN, basically an extension for probabilistic logic, where we once again found out that DMN is a great foundation to build user-friendly notations. As similar to CDMN, PDMN was a great way to build our notation, where it's automatically user-friendly and readable, or I should say, in our eyes, it's user-friendly and readable, and it uses this intuitive table-based format, right? So, okay, I've talked a lot about PDMN already. I would like to now show you an example. And for this example, we'll be using the earthquake running example, which is, I think, the de facto example within the world of probabilistic reasoning, where basically you have a 70% chance of someone robbing your house. There's a chance on a light earthquake and a chance of a heavy earthquake. Depending on the combination of these, your house alarm may trigger. And then if your house alarm triggers, there's also an 80% chance that one of your neighbors will actually call you to let you know that something is going on in your house, right? So that's what we want to encode. So first, what we have to do in PDMN is we have to define our variables in a glossary. Because PDMN has n-ary symbols, like I said for Problog, it doesn't only have Booleans, it has n-ary symbols and it has functions. We need to define these up front. And so basically what this means is that first we introduce types, which is a domain of values, such as we have a type person and a type intensity containing people and intensities, right? And then these types can be used in our predicates and function names. So for instance, burglary alarm and any calls are Booleans, just like in Bayesian networks, but person calls here is a predicate over person. So this means that you can view it as representing both John calls and Mary calls, but just in one keyword or in one word. And why we do this will become more clear later, but the main benefit is just that it's easier to write. if you have a lot of people, say you have 50 people, you don't want to write John calls, Mary calls, Frank calls, etc., etc., etc. And this is also another benefit. If your problem domain changes, say that you have a new group of people or a neighbor leaves or you move somewhere else, you just need to update the elements in your type and then you're done, right? So it becomes less problem input specific, I guess would be a way to put it. So this is our glossary. We introduce predicates, and then we also have a function earthquake, which will represent the intensity of our earthquake. If we look at decision tables, PDMN extends them in 3 different ways. So the first one, and this is obviously very obvious, probabilities. So for instance, here I have 2 probabilistic tables. One where we say that there's a 70% chance of burglary. This is just a very simple table with only an output. And one where we define whether or not our alarm triggers. One thing you might notice here immediately is that we did change the structure of DMN slightly, where we moved the output value to the top of the table, or in the gray row, as you can see it, and we actually replaced it by the probabilities in this actual cells below. So here, what you should read this as is, in the table on the right at least, you should read the first rule as there's a 90% chance of the alarm triggering if the burglary is happening and the earthquake is heavy. There's an 85% chance of the alarm triggering if there's a burglary happening and the earthquake is mild, right? So this is quite a big change, but it's in our experience, we experimented with many different formats. One of the better ways to represent this change. And of course, if you have tables with multiple output values, so here it's just Booleans in alarm. If you have multiple values, you put them all next to each other and then their respective probability in the cells. But I have more examples later. So that's the first new table type. The second table type is the choice hit policy. And the choice hit policy basically denotes that there's multiple values possible and each value has a specific probability associated to it. So here an earthquake can be heavy, mild, or none, but it needs to at any time be at least one of the 3, right? An earthquake, there's no fourth thing that an earthquake can be. And these are the probabilities for these values. And so what's important here is that these probabilities in the choice table actually add up to 1, because every possible value needs to be included. And so if everything is included, then you need 100% chance of in total, right? A better example for this table, maybe unrelated to the earthquake, is where you throw a die, right? So imagine you're throwing a die and it might be loaded, it might be biased. And if it's unloaded, you have a 1 in 6 chance of any value. And if it is loaded, you loaded it in such a way, of course, that you have a 1 in 2 chance of rolling a 6 and a 1 in 5 chance of any of the other values. 1 in 5, no. Yeah, 1 in 6, of course. No, I'm starting to doubt myself. 1 in 5, I need to trust myself. And so that's a quite interesting way, because here we have a decision that affects the actual probabilities, right? Depending on whether or not our decision table has bias as an input, or whether or not bias is true or false, will actually affect our probabilities. And this also means that any subsequent table which reasons on this die value, right? We might have a table that says if the die value is 6, then jackpot, will also be influenced by this probability, right? So that's what I meant with probabilities need to be continue to reason on. They need to be propagated throughout the system. Every subsequent table also becomes probabilistic in a sense, or the decision for each table becomes probabilistic. But I have a better example for that later. Then the third thing that we add is quantification, where basically if you have an n-ary predicate with n higher or than 0, you can replace that type by uppercase letter such as x or y, just denoting a variable, and then that means for every. So here you can see a table where we say x calls. So this means for every person holds that if the alarm goes off, they have an 80% chance of calling. And then the table on the right, basically the same. We just want to find out if anyone calls of our neighbors. So we just say for any person, if they call, then any calls is true. And this ensures that if at least one person calls, any calls will also be true.
What is the meaning of row with yes, this gray row?
Yeah. So yes here means, so like I mentioned earlier, we moved the output values to the top, right? So in a normal DMN table, you would have written yes in the place of 0.8. Here we moved it to the top so that the probability is actually in the output value. So here it means that there's an 80% chance of N calling, for instance, if alarm is yes, or if alarm is true. I have better examples of that. And we don't include a no here because, you know, by default, a Boolean has a no chance, or has a chance on being false that's equal to 1 minus the false for yes, the chance for yes, right? So we just drop that. So there's an 80% chance of it being yes, 20% chance of it being false, no, I should say. But yes, finally, in PDMN, we have the query table where you can also say, okay, calculate me the probability for this symbol. And this doesn't really hold any meaning. It's just for our solver to ensure that it knows what it needs to do, right? Okay, I have the full example here. Hopefully this makes more sense, right? So we have our glossary table in which we define the symbols that we use throughout. And again, this is important because we have these NRE predicates, so we can't just parse anything at random. We need to know upfront what we are expecting in our tables. We have a table that says there's a 70% chance of burglary in the left. The table that says there's a 1% chance of a heavy earthquake, 19% of mild, and 80% of no. There's if the alarm goes off, there's an 80% chance that that a neighbor calls, and there's a 10% chance that that they call if the alarm doesn't go off. In the bottom left, we have our probability for the alarm triggering when burglary and earthquake actually do happen. And then we have finally a table that just groups together if anyone calls, right? And then we want to query, will someone call? So we can then run the PDMan solver, which actually uses Problog internally. So the tool that I mentioned many slides ago is actually used internally, where we translate our PDMN tables to the Problog rules, and then we use Problog to calculate the probabilities. So this is the Problog equivalent, but yeah, I won't delve too deep on that. But here, basically, you can see the output that the Problog engine calculated for us. So in this case, there will be a 46% chance that Mary calls, a 46% chance that John calls, and a 55% chance that anyone calls at any given moment, right? When we don't know anything. But if we do know that any calls is true, so if you already know upfront, and this is where it gets interesting, right? Oops. If we already know that someone has called us, we have evidence for this, then we can have it calculate the probability of a burglary having happened, and then it actually turns out there's a 99% chance that a burglary happened if someone called us. So this is good to know. So imagine you're at work and someone calls you, you know there's a 99% chance that someone's breaking into your house, right? So that's what this is supposed to represent. Of course, there's a very abstract example with burglaries and earthquakes. So I want to show another example, which is a COVID example, which was very topical at one point and then a little bit less topical, and now is sadly becoming topical again. Imagine someone came in contact with one or more infected people, and you want to assess whether or not they had a high-risk contact, depending on their vaccine status. What's interesting here is that you might have come in contact with someone else, right? They might have notified you that they have COVID, but you might not know what vaccine they got, right? Even though that if we look at statistical data, it does actually influence on, it has an influence on their spread ability. I'm not a doctor, so I hope to be in a month, but a different kind. So it does influence the rate at which their illness spreads. And there's a cool way we can handle that. So first, we build our glossary. It's quite simple here. We have just people and we have vaccines. So here We have vaccine A, vaccine B, and no vaccine N. And then we have two predicates. One person is infected, which will represent for each person whether or not they are infected. And then a person contacted person, which will represent when two people were in contact with each other. So this is not too difficult. This is a very low resolution table. So like I said, you might not know their vaccine status, but what you do know is the statistical data from your country, right? And the statistical data might say that, hey, 36% of our population has had vaccine A, 63% of our population has had vaccine B, and only 1% hasn't been vaccinated at all. So instead of having this data be completely unknown and having to make a guess, we can actually say, okay, but we know statistical data, we can use these as probabilities in our model to then build the rest of our model on. And in this case, we might also not know our own vaccine because it's already been 2 years ago, you might have forgotten already. So it's nice to have a good estimation of this. So what we do then is we can add a table, which again is very low resolution, where you basically say, okay, if X contacted Y and Y is infected, then depending on the vaccine of X, X will also be infected, right? So if you are vaccinated with vaccine or with no vaccine, you have an 80% chance. If you have vaccine A, you have a 10% chance. If you have vaccine B, there's a 20% chance. That's the basic gist. Of course, like I said, we also want to include the vaccine that the other person had. So then our table becomes even larger, but more in higher resolution. So that's cool. Where we basically, we just enumerate all possibilities. So if I have no vaccine, then it doesn't matter what the other guy had. If I had A, then these probabilities. If I had B, then these probabilities. Again, it is a very simple example, but I hope that it conveys the idea of this probabilistic reasoning. Because again, here we can look at statistical data. We can look at what research says on these vaccination rates between people that have a specific vaccines, right? And we can use this to continue reasoning on. And what you can then do is say, okay, if I don't know any person's vaccine, the chance that Bob is infected, or in my case, that I would be infected, would be 10%. If you had high risk contact and the other person, you don't know their vaccine. So 10% is not that high, right? If you do know that the other person had vaccine A, your chance would go down to only 7%. I still don't know my own vaccine. Or no, sorry, if I know that my own vaccine is A, I'm sorry, then my chance would go down to 7%. So that's already becoming quite nice. I can sleep again at night. And then what's cool here is that you might, for the other person, not know that which vaccine specifically they had, but maybe you do know that they were vaccinated, right? Because they said it at one point. So you can also enter this as evidence. You can say my vaccine is A and the other person is not N. So it can be either A or B. And then your chance reduces even further to 6.9. Okay, so that's only a 0.1% chance decrease. But still, it goes to show that this can also have an influence. The more information you have about the actual situation, the better you can estimate this probability. And that's fun or interesting because you could imagine that you build a process around this where you calculate the probability of infection and say, okay, if your risk is below 5%, you can actually enter. And if you're otherwise, you're not allowed entry in a specific place. So you can make decisions or top level decisions in a process. You can make a decision on the probability that something happened or that something might happen. With probabilities, everything might happen, of course. And so if we look at actual COVID regulation, these are always very strict. These are always very hard. And by that, I mean, they don't take probabilities into account. Or they do take probabilities into account, but they hide it from they make some very large assumptions where they say, if you are vaccinated with A, your risk will probably be low, right? But here you can actually calculate it into something tangible and make an informed decision based on that. Okay, so that slide reappears. So that almost sums up my talk. Quite in time, I see. I just briefly wanted to compare it to the related work that I mentioned in the beginning. If you compare PDMN to Bayesian networks, and this is probably the more interesting comparison, because both try to be as user-friendly as possible and try to be readable and intuitive and graphical. So both are visual in nature. You could call DMN visual, right? But PDMN is more expressive because we have our NRE symbols, we have our functions, we have our quantification. And this means that for some of the more larger or more complex problems, you will have smaller models that are more readable and thus more maintainable, right? If you have less tables, there's less to maintain. And similarly, it's more flexible. So if your problem domain changes, like I said, if you have a new group of people, then you don't need to update many nodes. You can just update a few things and your model will follow suit. So that's the main advantage it has over Bayesian networks. The main downside it has, I see that it's not been added to the slides, is that it will be less performant for very large model. Bayesian models or Bayesian networks have really optimized algorithms where for Problog, while it is already quite fast, it can become sluggish for really large models because it has to calculate all these probabilities, so it only makes sense, right? If you compare PDMN to Problog, yeah, there the comparison is a bit easier. PDMN seems more user-friendly because we have this evidence from the DMN world that DMN is user-friendly. So it's not that far of a leap to say that PDMN is at least more user-friendly than Problog. But of course, Problog is more expressive. There's many things you can do in Problog that you cannot do in PDMN, but we carved out that segment of expressiveness of functionality that we feel is the most important while still being the most user-friendly, right? So there's a trade-off that you need to make when doing something like this, and we feel that we got it pretty good. We did it pretty well. We looked at a lot of examples and we tried a lot of models ourselves, and anything that you would want to model in such something like PDMN, you probably can model. And if you want to model something more complex, then it's definitely worthwhile to learn a more complex language, right? Such as Problog or a more complex system. And then both use the same engine. It's a bit weird wording to say that PDMN just uses Problog, right? So any advantage Problog has on the engine-wise, PDMN will also have. All right, I think yes, that concludes my talk. Nice in time. So I have more some interesting URLs if you are interested. At least there's an explanation on PDMN on our website, which you can find there. You can also just go to cdmn.be and you can find it from there. There's a the code for PDMN is available online. So basically, what does this mean? It's the parser for all the tables and then translating it into PDMN and then running or calling the correct Problog API to actually run it. We have a paper as well that you can read if you are so inclined. And then I just put my own website there. If you want to contact me for anything, then feel free to do it. There's a bunch of contact options there. All right. Thank you very much. I look
Okay,
forward to your
Simon.
questions.
Thank you very much. We have a question from Jen Purchase. I think you can read it in Q&A.
Yes, but I'll have to stop my slides real quick.
Okay.
Yeah, okay. There's a chat, there's a Q&A. It's loading. Really, any plans to support continuous random variables in addition to Boolean? Ooh, that's a we currently by continuous random variables. That's a great question. No.
Jan,
Look,
maybe you can elaborate a little bit.
Yeah.
Jan.
So
certainly, yeah. So this has been a really interesting presentation, by the way. Thank you very much for that. I wondered, you've got some very good examples here with Boolean random variables. I just wondered if you could extend that to support continuous random variables at all, and whether that's something you thought about and how practical it would be.
So for instance, you would want to say something that there's a chance of a price. So the
Yeah,
chance
you
of
want
the
to put a
price of oil
probability
is like,
distribution.
yeah,
Right, you want to put
yeah.
a probability distribution on top of a continuous quantity.
I think, but I would have to check with my more Problock inclined colleagues that Problock supports it, but it's yeah, it's very resource intensive. And so PDMN itself, so our notation, doesn't fully support it yet. But it would be interesting to look into it, definitely.
Okay.
And so how do I get a hold of this? Yeah, you can go to our website, and I hope that everything is clear there. If anything in the documentation is unclear, always feel free to send me a message and I can update it there.
Okay. And I just put some link over there that I want you to know. Probably you're not aware of this, but 10 years ago, two engines from Drules and Open Rules at the same time came up with business rules with probabilities. But our intention was a little bit different. We considered conflicts between rules, resolving conflicts, and we used defeasible logic for this, and we use probability only for this. You certainly go one step further because you can calculate probability of results. That's
Yes.
quite interesting. But I'm not sure if the same thing, you can do the same thing, for example, when we have conflicting rules. For example, you can say that all birds can fly with probability 60%, but penguins can fly with much higher probability, or cannot fly with much higher probability, but penguin is a bird. And then you can say that penguin can fly, but penguin in plane can fly with even more higher probability. So solving all these conflicts, is it possible with your approach also to do it without defeasible logic?
I think it's possible, but you would basically model as if it were defeasible logic, right? So I think that while it's possible, it won't be the best approach to use PDMN to do something like that. But yeah, I would need to look into it further, because it's actually something that I hadn't considered yet to combine defeasible logic and probabilities. But it's a really interesting.
I gave you a link, and similar, it also includes links to Drule's implementation, so you can look at this. But in general, it's really good. You actually, if we add probabilities to business rules, we would be able, with DMN, solve much larger class of problems, right? And you just gave very nice examples. And actually, even what you're doing now, asking to add this to DMN, we had the same request to DMN committee 10 years ago, extend to DMN with probability, maybe with different formats, but probably it's 10 years later, it's even more important. So hopefully DMN committee may consider this, but you can add this through standard DMN request channel. And we have also a question from Bob Moore. Look, if it's not continuous, what about discrete distribution with more than two values?
Discrete should be possible. So I showed the earthquake example where we had 3 string values, but nothing is stopping you from adding actual numbers there instead, right? So you could say that the earthquake has an intensity on the scale of Richter, I think, where you can say it's this number or this number or this number. So it's possible.
Okay, Denis?
Yes, very, very interesting presentation. I really like it.
Thank you.
Have you considered the big move here is to move into probability, but have you considered maybe looking at a more discrete decisioning aspect? So right now you're providing a probability, not necessarily a decision, and I'm wondering if you could use the interval reasoning that was added in DMN 1.3 and then the interval capability as an input that was introduced in DMN 1.5. So you could start looking at ranges as inputs and ranges and use all the range. They were introduced under the temporal logic moniker, but it's really interval logic that's being done there. And you could start doing some of that and reach to decisions. So that could be maybe a nice compare for you to do.
Indeed.
To see if you can do that in that way.
Yeah, no, you're right. But that actually it brings me. Thank you for mentioning that. That brings me to a different point. I think on my slide it was still incorrect, but I wanted to really mention that I don't necessarily think that standard DMN should have probabilities.
Yeah, you mentioned
In writing my thesis, I actually came to the conclusion that DMN's deterministic nature is one of the main what makes it so accessible, makes it so user friendly. You always know everything will have, if I add inputs, everything will have a value. If your DMN model is correct, everything will have a value will always be the same for every set of if my inputs are the same. I'm becoming less verbose as time goes on. I'm sorry, but so I really think that what DMN has going for it is that it's so simple, and so that's why I like making these extensions and not necessarily proposing to include them as well, because we can do it in extension as we please, of course. But if
yeah,
you
no, those are
also
very interesting extensions, and I
Absolutely.
think they do bring value in specific case. But I think in a complement to what you did by providing using the interval reasoning capability, then you could turn these into decision as opposed to just probability scores.
indeed,
Yeah,
that would be very interesting. All right, thank you. That I
yeah,
could really use that.
that's a good point, because if what just Denis said, it's in general, if you make decision in one decision table, the probability of, let's say, accept this application with probability 80%, and then another table can check if probability of acceptance is more than 75%, then do this, and if it's less, then go to manual evaluation of this application. So that certainly makes a lot of business sense, and it does not complicate really, because you're hiding all complexity. What you're doing good, that you're not talking in terms of prob-log, but you're talking in business terms, and that's what brings value. Okay, Simon, thank you very much. And we have your contact, so people probably can contact you directly. And thank you. We will take 5 minutes break, and our next presenter will be Helmut Simonis. Okay, I'll stop recording.